Hello everybody, today we'll be covering several concepts in physics about sound and light. So if you'd like, go grab a drink and a snack and let's get right into the video. Alright, let's start off with talking about sound. So first off, what is sound? Sound is pretty much just a vibration through compressions of air molecules that eventually reach our eardrums, which vibrate them, and that's how we hear sound. I'll show an example of that on the screen. So here we have a longitudinal wave. A longitudinal wave is, like I said before, just a series of compressions that continue these vibrations until the end of it. So let's say the cause of these vibrations was a clap. So on the left side of this longitudinal wave, I have my hand clapping, right, causing these air compressions. And on the right side of it, I have my ear receiving these compressions. So when I clap, like I said, it causes these air compressions that travel throughout the air with these vibrations, and then it eventually reaches my ear, which vibrates my eardrums, which causes me to hear that sound. Now let's talk about something more fun here. Let's talk about sound in instruments, or more specifically, stringed instruments. But before we can take a look at actual instruments, we have to discuss the variables that may change the output of this sound. Let's begin by talking about frequency. So as you can see here, we have our string, we have our oscillate. So we could change our amplitude, frequency, damping, and tension. Well, what we're really here for is the frequency, right? So if we just play this, right, you can see it's going very, very fast, right? Very wobbly, very nice. Wow. If we could slow it down a little, right? See, it's a lot slower and it's a lot longer. These waves are a lot longer, right? Let's go to the middle. It's neither long, neither short. It's just right in the middle, right? But what happens to the pitch of the sound when we change the frequency? So as we increase this frequency and as these wavelengths get shorter, right, the pitch of the sound increases, it gets higher pitched, right? And if we shorten those wavelengths and decrease that frequency, we get a lower pitch of a sound. Now let's talk about tension. So as you can see here, we have a string and we have our tension changing thing over here, right? So let's just play this as it is. We have our nice long, slow wave, right? Nothing wobbly at all, just a regular wave, right? Now if we decrease the tension, what happens? Those wavelengths are starting to get a little bit shorter and it's starting to get a little bit more out of hand, right? Now if we decrease all the way, then what happens? Those are really short wavelengths and it's getting a lot more wobbly, a lot more wonky, right? And although normally shorter wavelengths means higher pitch, in the case of tension, the lower the tension, the lower the pitch, and the higher the tension, the higher the pitch. Alright everybody, here's where the fun begins. So as you can see, we have our guitar, right? Right? It is what it is, it's just a normal guitar, right? But let's play both E strings, right? See, they're both E strings and we're playing the same notes. But if you noticed, this top string is a lot higher pitched than this bottom string. But why is that? Any answers? Didn't think so. Alright. I guess I just have to explain it. But as you can see, if we look at the string itself, this top string is a lot thinner than this bottom string. This one's a lot thicker, right? It's big, plump, juicy string. This one's just like a little skinny boy, right? So when we play this, and it's a lot lower pitched than this top one, it's because it has a lot more mass. It's a lot harder to move that. Therefore, the wavelength is a lot longer, meaning that it has a lower pitch. Alright, so for the next segment of this video, I wanted to cover string length and how that affects the pitch of the sound. So basically, some of you may be familiar with the very nice instrument called the violin, right? And some of you may not be familiar with another instrument called the cello, right? And so if you don't know what the cello is, it's pretty much just like a bigger violin. Think of it as that. Even though it may be annoying to some people, just to put it simply, a big boy violin, right? And so the cello has a lot of a deeper tone, has a much deeper tone than the violin. But what causes this, right? Let's watch this video as an example to hear that deeper tone first off. Alright, we're gonna pause it there. If you want to listen to more of this, I'll leave a link in the description. I recommend checking it out if you like some chill music or if you're into Ghibli films or something. But link in description. But anyways, as you heard, the cello, the instrument the girl is playing, is a lot deeper than the violin, the instrument the man was playing, right? And so, what makes it deeper? So, as we know, cello is big boy violin. So, big boy violin needs big boy strings. So, these big boy strings are a lot longer than the normal violin strings, right? And so, because of this, the wavelengths are also longer. And what happens when wavelengths are longer? The pitch gets lower, as we all know now, right? So, if the wavelengths are longer, pitch gets lower. Strings are longer, pitch is lower. Simple as that. Now, I don't know about you guys, but I'm sick of sounds. Let's get straight into the next topic, aka lights. And if we're talking more specifically, we're talking about reflections and refractions and how they work with different types of mirrors. Alright, let's get into it. Alright, so first off, we got reflection and refraction. So what is reflection? Reflection is when a light source produces a light ray that bounces off a mirror and it bounces back at an angle. And so when it comes to plane mirrors, they also known as just like a straight standard mirror, right? If it hits a plane mirror, it always bounces back at the same angle. So the angle of incidence, or the angle that it hits it at, is always the same as angle of reflection, right? And if it hits a concave mirror or a convex, there's a lot more rules to that, but we'll get to that later on. As for refraction, pretty much refraction is when a light ray goes through one clear substance to another, and that second clear substance either has a higher density or a lower density, right? And so if it has a lower density, the light ray will point upwards, right? It'll tilt upwards more, right? And if it's a lower density, if it's a higher density, then it will tilt downwards since it's gonna move slower, right? As an example of that, I'm sure everyone's done that at some point. When you hold your pencil behind your water bottle or your cup of water or whatever, right? You notice that your pencil or your pen or whatever you're holding looks like it's bending, right? That's because the light is moving slower in the water than it is in the air, right? Or behind the plastic. So it looks like it's bending because out of nowhere, it's just moving slower. Now let's apply these rules to convex and concave mirrors. So as you can see here, we have our concave mirror, right? And the special thing about this mirror is that it could either have a virtual image or a real image, right? And so a real image is when it's in front of this mirror, right? When it's over here on this side. So this right here is actually currently a real image. It's just inverted, right? So as long as it's over here, anywhere over here, it is still a real image, even though it may get larger, like further and everything, it's still a real image. But the second it crosses this focal point, it gets on this other side of the mirror, it's now a virtual image, right? So now let's talk about the reflections. So as you see here, when it goes parallel to the mirror, it goes straight to the focal point. And then when it goes straight to the normal, it bounces back like a plane mirror, just straight the same way it came. And then if it goes to the focal point, it goes back parallel to the normal. Alright, now let's talk about our convex mirror. So unlike the concave mirror, convex mirrors can only produce virtual images, right? So that's because this image is always going to be on the other side of the mirror no matter what. No matter where I move it, it's always going to be there, right? But let's talk about the reflections. So as you can see, this ray right here looks like it would have, if it continued, it would have went through the focal point, right? And that's why it comes back parallel. This one goes parallel, comes back as if it would go to the focal point if it continued, right? And this one goes to normal and continues on the same way it came, right? It's pretty much the same as a concave mirror over here. It's like the same rules, just applies as if these lines were continuing. Alright, we're done for today. Make sure you guys have a good one, and I'll see you in the next video. Easy.